folks, how's it going? I can already see the chat, going nice and active. So that's awesome. I'm sorry, Yash, you're facing problems with the audio. I don't know if I'm audible right now, but I think YouTube is a good suggestion, as we said. But I can already see so many returning hackers, and that's always amazing. Hi there, Sined, Ria, and Wei and Yash, of course. Wei is another really nice, person who's almost always there at my streams. That's awesome. Anurag's back. Hi there, SKB. And then there's JJ Chan joining in. Then I did see another familiar name. Shivadeep is back. That's awesome, folks. All right. I am so glad everyone's back with the energy to do electronics part two. That's awesome. So, as you can see, as promised, I fixed my lighting. I am slightly more visible with a little less fancy background as well. And it's getting colder in Pune, so please ignore me coughing. But all right, folks, let's get started. So, first and foremost, you know the drill. Make sure that you've checked in and registered. So, in case you all are new here, I'll quickly show you the procedure, which I did not last time. So, I'm gonna take the link that I shared earlier. Let me quickly paste it back again in the chat. Also, I've also pasted the check-in link in the description. So in case at any point you want to find it again, you can find it there. And it's also there on Discord in the last announcement that I have made in the Global Hack Week channel. So you all are all covered. And there you go. That's the link. I'm going to quickly open that link in my browser as well and check in for my session myself. So share screen, Chrome tab. All right, so I'm going to register and check in very quickly. So I hope my screen's visible. No, it's not. Well, I need to remember. So over here, there was the register and check-in button. I've clicked it, and when you click on join online event, it should take you to Twitch, which is right here. So yep, that's if you do that, please do that because you get bonus swag, and I would hate for you all to miss out on bonus swag. All right, folks. If there are any questions regarding check-in, keep them, coming. I'll answer them as we go. But we're ready to start with day two. So let me quickly start presenting my slides. We'll go over day one very quickly, and for the folks joining in for the first time, I'll give a quick introduction of what we're up to. Right. So let's go. Slides, share. And there we go. Is my screen visible? I'm guessing not because I've not shared it. There we go. All right, I kind of like this layout, but I'm going to go ahead and change it to this. Into electronics 2. Again, in case you're here for the first time, I love talking about electronics. I love talking about hardware, even though that's not my main job right now. I am an electronics student, passed out as an electronics student, and I've been working as a firmware developer for all the internships that I did before this current work commitment that I have. But I always talk about IoT. I talk about wireless connections, and since this is Beginners Week and we're celebrating getting started with new technologies. I decided to take another step back and start right at the basics of, where we start looking at the building blocks of the circuits that run all hardware, right? And yesterday we covered like a lot of hardware where you all went around the house, found some things. We're going to be doing that today as well. I told you all to keep active components ready. So awesome. Let's get started. All right, Shivadeep, I agree. The way if you saw how awkward my table is, it's like right weirdly like angled, diagonally angled in my room. It's funny, but then I might just send you pictures later in Discord. I'm so glad you can see Yash. Just make sure that you're in a train station. To just make sure you're not out of resources. Okay, just it'll be recorded. Don't worry about this. All right, let's dive right in. So, in case again you're joining for the first time, hi, I'm Ritvy. I've been a coach at Major League Hacking for over a year. and 3 more months. This is exactly a year ago that I started taking streams. My first stream that I took was about IoT, and now this is about electronics. And I cannot think of a better way to start my year. Uh, and yeah, so I'm a maker. We already covered that. And I currently work as a community manager at Blues Wireless, which is also a cellular IoT company, although my role is, of course, very different. But okay, so we spoke about passive components yesterday. We'll go over a quick brief. You all can remind me what components you all posted pictures about. Then we will start talking about active components because it's a huge active components is a really big, it's a very big umbrella term. A lot of things come under it, and we look into it. Next, we'll do some circuit analysis, right? Circuit analysis, as in we'll just look at some graphs, which can get a little boring, but I promise you, I'll keep it human. And instead of showing you a PPT, we're just going to Google it all ourselves. We'll find different articles, and we'll see how things differ over sites, and that way you'll also learn which resource to trust, right? And if you've joined my streams before, you all know I love talking about, especially when I talk about components, is data sheets. So we'll look into the data sheets of some of these components and see how these analysis of the components vary. All of this we'll do for passive components because it's much easier to keep a track of the type of data sheets that you're coming across. Isn't it's more generic, right? And then we look into my another favorite subject, microcontrollers. I'll show you a couple of microcontrollers, and you'll find me devices in your home that use microcontrollers. You are surrounded by things that use microcontrollers. Okay, I'm not kidding. The amount of microcontrollers around you, and when I show you how they are microcontrollers, should baffle you, hopefully. If not, then you're already a pro. All right. And then of course, we will move on to making our own circuits. So here's what I'm going to do. It is 9:45 a.m. on my clock, right? So we will wait. We will talk about things. We'll post pictures until say the next 40 minutes max, and then we'll go into circuit making because I realized that took a little more time yesterday. So today, the things that we discussed yesterday, like current stays constant in which kind of circuit, voltage stays constant in which kind of circuit, why would you connect something in parallel and not in circuit, and vice versa. Some basic things. We'll actually make these circuits and see how the things differ, the values of these parameters differ. And then we will I love this, Yash. You should absolutely do that. Exactly, Jackson, especially in cars, which it's crazy how you're surrounded by embedded systems. But yeah, so we'll make our own circuits, we'll do some parallel, and A Jackson here is our in-house pro. So in case I don't answer the questions, he's always there to answer your questions. And yeah, let's get started. So yesterday we covered something called analogies. We'll keep that going, right? So every time, so I'm gonna need you to remind me what analogies we came up with for passive components. Now that you've actually used the passive components and you know what it actually means to use passive components, right? So we'll do a quick 5-minute analogy round. What are passive components? Come on, quick analogies, people. I'm going to give you all 3 minutes on the clock, and I want good analogies of what you really learned. It can be, again, I loved the character references, I loved the insects references. So come on, let's get this going. I want a quick analogy. I'll go with the first 5 answers. So let's get the first 5 answers, and then you know what? I'll send a screenshot to Mary to be able to present it in our daily GHW stream. I don't want examples. I want analogy. How do you associate a passive circuit? If you wanted to explain what a passive component is to a 5-year-old or a 10-year-old, or someone who has no clue what electricity, how electricity works, how would you explain it? Oh, this is a completely stolen idea, by the way. There's this really cool YouTube series on Nacho's channel or Wired channel, where they have this thing where they explain the concept to a 5-year-old, to a teenager, to a college student, and to a PhD student. Can you explain, Sachin, how a train? I don't want example, folks. I want analogies. Remember, I told you the idea, my analogy of a passive component was a couch potato, someone who won't move until someone who does nothing except if you give it like power. And this moment you take away power, it's back to its original state. If you give it too much power, the worst it will do is break, but you can't change it. Exactly. So come on. I want good analogies. Can you quickly tell me if you had to explain a passive component to a 5-year-old or a 10-year-old? How would you explain it? What's the example you would give, and would you compare it to? A Ferret wheel. I love it. That great example. So how would you that's exactly how it makes sense, right? Hamster gives it or a ferret. I'm assuming it's the hamster wheel. Is it similar to that way? A ferret wheel? I'm gonna look that up. I'm pretty sure. Ferret wheel. Yep, I imagined it correct. So yeah, so the ferret or the hamster runs on it and gives it energy. It works. If it runs too fast, it'll probably break. If not, it'll stay. Oh, that is very, very deep of an analogy, but I like it. I don't think, but again, you need to keep it a little simple. Like one word, like one association you make. When I say a passive component, what is it that you associate it with? All right, I'm just looking for two more answers and then I'll move on. I know I can pester you all a lot. Strings. I like the association. Nice strings. I'm imagining a instrument strings because you have to give it energy again. I don't understand the cue example. Uh, all right, so now you all are just naming objects that cannot move. But I wanted someone yesterday gave me an example of a character or a I think someone gave me an example of Sheldon, and I love that. I love the Big Bang Theory example. So passive components, Yash, are basically anything that needs energy. So resistors, capacitors, inductors. These are some examples of passive components. Transformers, right? They have some parameters and they have some capabilities, but they don't do anything except they are given power. They can't alter the power. They can't, as in when I say alter, they can't increase it. They can always control it, but they can't really change the actual amount of power going through. Again, love this example. This is what I was expecting, folks. Tony Stark's assistant. Although I think Pepper was a little better than that, but okay. But are you talking about Friday and Jarvis? If you're talking about that, then it makes sense. All right, folks. Awesome. Let's move on. I am expecting some better analogies for active components as we get there, but that's okay. So, okay, you already went around and found them. Yes, Yash, LED is actually a passive component, and RIA and IC is an active component. But then again, it depends on what the IC does. But mostly ICs are active components. For example, integrated circuits, right? So, integrated circuits are basically, it's like you asking me if a PCB is active or a passive component. So while the PCB itself is a passive component, what's on the PCB can be an active component. So similar way in IC, if it is an op amp, yes, it is an active component. So you'll have to look at the specifications of the IC. Okay, I like the examples. I love the examples. I'm glad you all found it. So you all already did this. You all went around the house and found it. And now we're going to be talking about active components. So we have spoken a lot about active components already. So, quick, give me examples of active components, and then give me analogies of active components, preferably in the same answer. All right. So, I'll start. Right. So, the way I look at an active component is I loved the Big Bang Theory example you gave. So, I came up with that. I think of Amy. as the active component because she actually kind of, changes the entire dynamics and increases the whole, dynamics of the group, right? So that's my example. That's my analogy. My example of an active component is the op amp that I spoke about, an amplifier. An amplifier literally amplifies the current or the voltage, and hence increases the power, changes the gain in the circuit. So diode is actually a passive component, Sachin. Zener diode, LEDs, they're all passive components. Transistors, on the other hand, are active components. Oscillator IC. All right, that's an interesting example. Generators. Now, again, generators. You know what? I'll give you that. Generators is a great example. But inside the generator, if there is a tiny transformer, remember that is actually a passive component. But yes, generator overall is a great example. All right, folks. Now I'm looking for analogies. I've got some great examples, and see, this is a good analogy. Thank you, Yash. I like this example, analogy. Great job, Siner. I love this again. Great association. Especially, I love it when you associate things to MLH. That's the best way to learn. All right, I'm going to give you all another minute on the clock to come up with some more, and then we'll go to Tinkercad and we'll see a couple of active components, and then we'll start looking at data sheets. That is another good example, analogy. What's wrong with me? Analogy, and I think that applies to every mom in the world. Yash. All right, folks. I love the analogies as well. So before we move on, next I want you all to start opening Tinkercad, and I'll start. We'll start pushing. So what we'll do is we'll make notes. We'll make passive and active, and we'll go classifying components as passive and active. All right, and absolutely, Jackson. Exactly. But then that's the whole point. We're looking at components themselves. So the component itself, we're classifying. A bigger circuit, of course, can be anything, and we'll look into that, right? We'll look into ICs and stuff. Awesome. Yes. Actually, the next point I was just about to ask you all is to do the same thing we did yesterday. Come on, go around the house, click a picture of an active component, and put it in Discord. All right, and it's again 9:57 on my clock. I'm gonna give you all until 10:05, and by then I want everyone to have a picture of an active component around the house, or rather something that uses an active component. Right? This is much easier. All your switches, or not your switches, all your power sockets are active components technically. All right, think on those lines and see if you can find something around your house that is an active component, uses a specific active component, and ideally, no. Because when you're talking about components, when refer to components today in this stream, I'm referring to the tiniest building blocks, right? I mean, if you break them further, you should either get materials used to use the make the component, or like something like gates. The reason I say gates is because I've been referring to the ICs a lot, right? Folks, please don't miss out on college because of the streams. Perfect example, Yash. Yes, a motor is a passive component and a battery is an active component, right? So that's what I mean. So if you break down a motor, you'll only find the materials required. If you break down, let's say, a drill machine, there's going to be circuits, there's going to be a lot of components building up to that, right? When I refer to a component right now, I'm referring to the absolute tiniest building block of an embedded system. All right, folks, I have my eye in Discord. I am looking for pictures, waiting for pictures. And the moment I start seeing them, we can start and move on to Tinkercad. A transmitter, yes, a transmitter will be an active component because it actually, you know what, on a second thought, yes, a transmitter is an active component because it can amplify and it is changing the gain that we're sending. My Discord ID is @3. So as soon as you go at you type an ad and go for RITVI, you should be able to see me. You should be able to tag me. It says from MLH, but I'm gonna put it in here anyway. Hashtag 2646. There you go. All right, folks, I'm waiting for pictures. If you're posting the pictures in your guilds, which is perfectly fine, just tag me because there are like such amazingly active guilds. It's going to be very hard for me to find where you all posted it. And again, we've established I'm not the best at finding channels in the right time. Awesome. Ajax has posted a processor IC chip, which is great. You send it on Discord, Beginners Week Lounge, or your guild. In case you're sending it in your guild, tag me. I know Yash is sending a picture, which is great. I like the assumption. Yash has posted a TV on this train station that he's at, and he's like, it must have an active component, which is a great assumption, which is an assumption I'm happy to give him. Yes, there are voltage regulators and ICs on every circuit, so go for it. They're not. So here's the thing, Uptalk. They're not active components themselves. They contain components that are active. So yes, go for it. Till the time you know you're not considering the AC remote itself as a active component, I'll take it. Go ahead. Ooh, adapter. Awesome way. I love the examples. Way here went ahead and posted a charger adapter, which we mentioned. So we know that it's converting AC to DC and hence is actively changing the numbers when it comes to gains and powers. That's awesome. All right, folks, it is 10:01. I'm going to give us another couple of minutes, 10:04, if people want to post more pictures about active components. And then we want to Tinkercad. This is great. I love the engagement. I love you all are so enthusiastic about this. Oh, Tactic actually posted an AC remote. I love that. Awesome. Are you all posting in your guilds? Because if you are, please do tag me. Switchboard is the best example. It's one of the most basic examples. It itself is very much a basic active component. So go ahead. But then remember, when you're looking at the switchboard, the switches are passive, the sockets are active. Makes sense, Sachin? But you go ahead and post it anyway. We'll circle it later. Awesome. Sachin gets that. Amazing. Great. So I am looking at Discord. If I see a couple of more pictures, I shall mention it. If not, we are ready to move on. All right, I don't see any more pictures coming in or comments, so we are ready to move on. Let's go to Tinkercad in case you all are joining the stream for the first time. Tinkercad is a very nicely made simulator and circuit builder for especially beginners. You, I mean, you can do amazing stuff with it. It's just that it's great for beginner, like starting off as well. So try and sign up in the next couple of minutes if you're here for the first time. Give me a heads up if you want me to wait. Always happy to do that. All right. Okay. So we are. I'm gonna start sharing my Tinkercad in just a minute, and that's what we're gonna do. We're gonna literally open a new circuit board. So if you all sign up for Tinkercad, I'm gonna quickly show you how your screen will look like. So stop sharing. I'm gonna present share screen, Chrome tab, Tinkercad. So these are all my circuits. I'm gonna go ahead, create new. I'm not sharing my screen, am I? I haven't worked with StreamYard in a bit now. You know what, Yash? I think you can. You can use Tinkercad on your phone. Just open it in your browser, in your phone browser. I'm pretty sure you can use it. If not, then you can always try Wokwi. You will just qualify sensors instead of components. All right, folks. So, uh, again, anything we do, feel free to post this on Twitter and tag me, of course. I would love to retweet what you're learning. And great. So Tinkercad, this is what your dashboard should look like. You can, if you go in all designs, there'll be a ton of more things. You can see I've been playing around with a lot of things here. I also tried to make some 3D stuff. Surely, you like long time ago. You can see 2 years ago, 4 years ago. But anyway, you need to go to your circuit board, click on new, click on circuit. Now, Tinkercad does this really good thing where it just gives a nice name to your project. You can always rename it later. I'm gonna leave it as it is because I like the fun names that it gives. All right. So a couple of things that I wanted to cover yesterday and I completely forgot is what I'm going to quickly do before we get started. But I'm going to first wait for another minute for you all to give me a heads up that you're on the same page. So I am looking at Yash, Sachin, Aptak, Vay, Siner, Salad Mama, or you know what, Salad Mama, if you're in college, don't bother. Ria, A Jackson, if y'all are following along, I'm gonna wait for y'all to give me a heads up that y'all are on Tinkercad, you're on a new circuit and everything. All right, Way is there. Perfect. Way is already there. So I'm gonna go to my yesterday's circuit very quickly before we move on. Uptak is ready. Awesome. Mm, let's see. Wow, we all chat a lot in the beginners week lounge. I'm having trouble finding yesterday's pictures. That is very kudos to you folks. Great engagement. Should have I found it? Yep, almost found it. There we go. All right. So yesterday, no one did that. I just wanted to see if anyone actually found out what I meant by good practices of building circuits. Uh, we can use it, A Jackson. Again, if you have already used it at some point, you're welcome to come on stream and explain what you've done, okay? And that applies to everyone. If you all are done and you all want to come and share you've done something differently, go right ahead. I'll send the stream link to you all. I can send it in the chat itself, or if you all want, you all can create a ticket in Discord, tag me. There are tons of tickets. I'll send you the stream link there. All right. Everyone's ready. Awesome. If there's anyone who needs me to wait, let me know. We'll always do that. Okay. Okay. First, let's start with good practices, right? So let's say I'm connecting a simple LED to the battery. All right. Here's the thing. Right now we're building very simple circuits, so you don't really care. But the moment your circuits start getting complicated and the more you have, wires flowing through, you want to be able to differentiate and be able to debug easily and hence identify where the wire is coming from. So as a good practice, and it's a great thing to make a habit of it from now, especially if you ever plan to continue this, right? Always make your plus voltage wires red, right? So every time positive goes to positive, the negative should always be black. So now, okay, so this is the general practice, right? So I'm gonna click on my LED. and flip it and then rotate it so that it's easier to look at. There we go. Alright, so this is what my circuit looks like. Now this is a very good practice. Okay, red and black. Now tell me, is the screen too little? Okay, let me see if I can increase it. Oh, you mean your phone screen? Okay, never mind. Fair enough. It's okay, Ash. You can do it once you are in a stable place with a good connection and a laptop. All right. And I asked you to follow it later. It's okay. All right. So a good practice, of course, is red and black. Now there'll be multiple times, especially if you're working, with actual wires, that you don't have red and black. What do you do then? The darker color is always the ground. All right. So if you have, say, yellow, orange, orange becomes ground. If you have green, blue, blue becomes ground. The darker color always becomes ground. And when I say ground, I mean the black wire, the negative connections. All your negative connections should be in one color. When I say negative connections, I mean so all your components, right? If you look at the components here, especially sensors and stuff, all of them have something called VCC, which is your voltage, your power plus, and ground, your ground. And then there is always the third pin or the fourth pin, which is the communication pin, which sends out and gets the data. All right. So all your VCC wires and all your ground wires should be connected, the darker to the ground and all the lighter ones to the VCC. Ideally, red and black. If you don't have it, the darker colors goes to ground. Fair, everyone on the same page? All right, so we will try and follow the practice today. Please, pester me if I forget it myself. All right, so let's get rid of this. Let's get rid of this. And we're going to do what I said. We're going to quickly go around and start qualifying things as passive and active. All right, so I'm going to quickly pick up a note over here. These are going to be my passive components. My passive components, and these are going to be my active components. All right. Okay, so I'm going to start picking up random components and classifying them. I've been using the wrong word before this, haven't I? Anyway, so now I'm using the right word. So I'm going to start I'm going to start classifying the passive and active components. So if you have two LEDs, way any color can go. Usually, if it's positive to negative, you can use something in between, like blue, orange, anything. So what happens in your PCB designs, there are tracks and stuff, so it's much easier to keep a track of. The reason why VCC and ground especially is very important. That's a very different concept. Live wire and neutral wire, that's an AC concept. The first thing that we spoke about yesterday is usually electronics are fairly DC components, almost always, right? Except maybe adapters and stuff that are actually changing the current and changing it to DC. All components almost always use DC power. So the reason why it's very good practice is when you start using components real time, you'll realize it is so easy to connect it in the opposite way. Especially another reason why it's very good is because, since A. Jackson already mentioned breadboard, I'll just show an example, right, how it works. So this is your breadboard, right? So what usually happens is, I'll quickly explain how a breadboard works. So in a breadboard, all of these, my tab got lost. Give me 1 second. All right, so all of these components you see, right, they're shorted like this. So if you connect something here, automatically over here, if you connect another wire, they get connected. Over here, though, the shorting you can see, right, the green line that's popping up, this entire green line is shorted. That means if you connect something here and then connect something here, they get shorted. So usually if you see bigger circuits on online or in tutorials, you'll see people, what they do is usually they'll put their battery VCC here and ground here and then connect everything over here, and everything will be the same color. Because if you don't do that, and let's say you're using random colors, and let's say you removed a component and you're putting it back in, it is a very high probability. I cannot tell you the amount of times you can just burn components by connecting them the wrong way. Now, usually sensors, especially right now, if you look at sensors here, that we might have. So let's see. Mm, 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 mm. Stop simulations. So if I look at sensors here, any sensor, right? If there's PIR sensor or anything, these all these all have diodes. So not this one, two, and three. If you all look at the circuit, actually, I'm not sure if you'll be able to see here. No, you can't. But over here, VCC and ground behind, there's a diode. So if you do connect it the wrong way, you will get like a 5 second, 10 second gap to realize that it's wrong. And how would you know is that the diode will be heating up like exponentially, right? The problem comes when you're using components like these, which have zero protection, right? So the moment you connect them on the other way around, the circuit's gone. It's completely gone. Did I miss a question? Oh, the app. Let me send you a link as well. Delicious. That is an interesting username, I must say. All right, there you go. All right, awesome. So, does that make sense, Way? So, what you connect between LEDs, between sensors, is completely your thing. You can decide your conventions. VCC and ground, though, is a good practice because I have done it, and hence it's more like a, I've learned the hard way, so I'm saving you all the trouble. All right. You know what? While we have the breadboard here, I'm going to go ahead and classify it as a passive component. It's when you think about it, breadboard is not really a component at all. It's just wires. So if you're qualifying wires as a passive component, you can qualify wire as the breadboard as a passive component. So breadboard is a passive component. All right. See, that's the thing. Your Raspberry Pi is a very sophisticated circuit. It expects, so that's what we call idiot proof, right? Like, if you're making something for beginners, you know they're not going to know a lot of things. So you kind of try and foolproof it as much as possible. So, go ahead, Wombo Combo. I'm looking at the chat if you have a question. And if you want to join on the stream and ask the question, you're more than welcome to do that, right? So, Arduino, Raspberry Pi, why are they so famous? Because they have actually tried to make it a little more foolproof and a little more idiot proof than components themselves, which is why when you're getting started, you usually get started with an Arduino or a Pi, not directly with, like stuff that you can blow up rather easily. You know what? I would love to help you. So if you ever, I will be staffing an FPH very soon. So you can ask me the question there. You can ask me, you can put your trouble in Discord right now. Or I would suggest asking your fellow hackers. So put the question, and Yash, I know, will be able to answer it. I know a couple of other hackers in the server that will be able to answer it. If they don't, tag me again and answer it. Sounds good? Raspberry Pi setting up is very easy, and if you can get back to me by today evening, I can just show you the entire process tomorrow. I have a new Raspberry Pi that I want to set up as well. So let me know. All right. Okay, folks, we're going slow. Let's speed up a little and quickly qualify. You know what? We'll just take like, see, I knew I was using the wrong word. Classify, not qualify. Classify all the components as active or passive. So I want suggestions, or if anyone wants to come on stream and do it themselves, I'll be more than happy to see that. If not, until then, I'm just going to quickly go all basic components and start classifying components as active and passive. Capacitor, polarized capacitor, diode, Zener diode. By the way, folks, diodes are basically just, they have the same structure as LEDs. Are you all aware? I hope you're all aware. It's very fun to see how they work. All right. Then I have push button, potentiometer, or they're calling it a wiper. Oh, by the way, folks, I figured out what we were doing wrong with the switch yesterday. I'm supposed to connect the switch like we connect the potentiometer, voltages, and the input and the output goes right in the center. I'll fix that in our yesterday's circuit as well. All right. Hmm. Flex sensor. Folks, where will the flex sensor go? Where will the sensor go? I'm waiting for some response. Okay. Where do you think the flex sensor will go? That is such an interesting fact, Yash. Thank you so much for sharing with us. Oh, is that so? Then I suggest using Bellina Formato. Uh, Try using Bellina Formato. I usually use that. That should fix your problem. Is flex sensor an active sensor? All right. So way flex sensor is basically it will tell you the angle. So if this sensor is ideally like a tall sensor, and if you twist it, it's going to give you a change in the voltage, and it'll tell you the angle of it. You know what? I think I can pull one up very quickly until you all decide whether or not it's a flex active component or a not active component. That is a great answer, Yash. You're getting very close. Yes. Not always, though, when you think about it. Not always. Specifically, this sensor, maybe. Here you go. This is a flex sensor, folks. I actually have two different sizes. So, when you change this is actually used. So, one of my seniors actually created a project with this, and with the help of, so they put flex sensors on gloves, and with the flex sensors angles, they could tell sign language. And that was actually a very cool project if you all want to think on those lines. They, of course, made it as a simple project if you all want to really make something big out of it. So that's a flex sensor. Oh yes, this is a very good suggestion, Yash. Yash and Alvin are good at setting up pies. Awesome. So Way agrees that it's a passive component. Wombo Combo, the emulate server, and I think use the Python Pros Guild channel so that your communication stays in one place. Or I think they have a hardware thread going on as well. All right, folks, awesome. So we all, I mean, three people, but they've decided that a flex sensor is a passive component, which is great. All right, so next component, force sensor. Same thing here. I have a force sensor. I actually have the same force sensor that they're showing as well. Found it, but this is good enough. So this is a force sensor in my hand. Same logic. So we'll put it here in passive components. All right, this is going to be fun. So photodiode. Okay, these aren't really thinkers. All right, IR sensor. Folks, where does IR sensor go? What does IR sensor do? So an IR sensor usually has two LEDs, okay? And not this one specifically, but you usually have a photodiode and a sensor diode. All right, and what happens is first the photodiode sends a beam. The sensor diode then absorbs the beam, and based on the voltage received, it gives a value. Exactly. So there's a one emitter diode. They're both LEDs of sorts, and then there's a photodiode and there's a photosensitive diode. So the photodiode sends out a beam, the photosensitive receives it based on the strength of the. So the strength of the beam will depend on the space and the color. right? So IR sensors is usually used for detecting contrast. So if it's darker or lighter, the beam will change its value, and hence you get a 0 or a 1. So what so yes, the emitter diode is what it's infrared, it's actually normal diode, it just emits it at a higher frequency. The photodiode though is what is sensitive to the IR rays. But what do you think an IR sensor is it a passive component or an active component? That is a good guess. That is a very good guess. I'm going to wait for a couple of more folks to form some logic. Emitter would be active. No, emitter is also an LED, so it's not active. Don't worry about that. So this particular one that I explained, this one is an active sensor. But the one that you see on the screen right here, you can see it's only a receiver, right? It only receives and gives a voltage value based on what it's receiving. So this particularly is a passive sensor. On the other hand, something that is sending and receiving, like your ultrasound sensor right here, will be, you can guess, because this is sending something and receiving something, an active component. Does that make sense, folks? Exactly. It is sending a beam, right? So it is sending a beam, getting back that extra power that it's sending back is basically what it's changing. So it's generating voltage. Exactly. It has an IC on it. It has actually an IC on it which is helping it do that. So yes. I'm glad it made sense, right? So an ultrasound sensor which is sending something, then receiving, and then based on that generating a voltage becomes a active sensor. Your flex sensor and force sensor, on the other hand, aren't really sending or receiving. Based on the pressure, they're just changing the resistance, like your potentiometer, basically, which is why they are passive components. All right, that is awesome. Okay, let's see what else do you all want to classify. Use the right word. So this is a good one. You see these neopixels and you see these LED circuits, right? Where would you qualify them? Classify them. Where would you classify them? The IR sensors. So yes, there are some types of depth sensors which use IR, but the ones that I spoke about are specifically used for contrast sensing because the strength of the reflected changes on the color. So if it's white, it gives a brighter, it gives more voltage because there is an LDR on it, and based on that, not LDR specifically, but an IC which is sensitive to the amount of light that is reflected back. Which one, Sinead? The LED circuit or the IR sensor that I spoke about? Whenever you're ready, Sinead. All right. So I'm just going to go through here and see motors. We know that they are passive. Hmm. What happens to a piezo? What is a piezo sensor? What does a so piezo? This is basically the one that creates sound, right? Hmm. All these batteries, active components, microcontrollers, not components. So do not classify them. Okay. Nice. Now we're on to the part which is my favorite. So our ICs. Now we're going to start classifying ICs. The ring, okay. So the ring here is something called it's basically a neopixel ring. All right. So what a neopixel ring is basically, so neopixel, this term particularly was started by Adafruit, and what it does is it's a bunch of LEDs, right? And they have already made a circuit for you, and you can now control that circuit, or rather that driver, in a certain way to create different patterns and different use cases for that LED ring. So instead of you getting 5 to 10 LEDs, creating a circle and then creating a driver and connecting them, they've done half the work for you. So let's say at any point you want to have a circular display of LEDs and play patterns on it, or create a a project which has a round surface, and you want something, a pattern in it. They've done half the work for you. You can just take this, connect it to your microcontroller, and start controlling it and playing around with it. It is because there's a driver attached to it, if you consider it entirely as a component. But what I was looking for is this. This is great, Yash. So I've said, right, that right now when we look at components specifically, we're looking at anything that cannot be broken down. So ideally, even the sensors that I classified, it's more to explain the concept than actually what I mean when I say a component, right? But which is why I'm happy that we've come to the ICs now. Exactly. Lightsabers and neopixels come in different this too. So the reason it's not passive, Yash, is because there's a driver in it which is actually controlling the power gains and being able to change the power gains with a voltage regulator, because the driver has that. Make sense? So if you consider that a component, it's definitely overall active component which can be controlled, right? Now let's look at ICs, right? So I'm going to quickly classify one IC, which I am very sure that now you all know. This is an op amp, this is an amplifier, and hence it's an active component, right? So I'm going to quickly pick up the NeoPixel ring, put it under here. So this is an IC. And now we look at data sheets and understand how data sheets work. All right, this is awesome, folks. So let's quickly create a new circuit, create a new circuit on Tinkercad. I'm going to quickly explain parallel versus series, and then we'll go into looking into op amp data sheet. All right. I really want to get through the part where we read data sheets together. In the next 30 to 45 minutes, because tomorrow we'll actually start using microcontrollers. We will read an entire data sheet of the microcontrollers, read all the components on the microcontrollers, see whether they're active or passive, right? Exactly. This is what I meant by analogy. They're basically biological cells. Now, the kind of cell you qualify it, for example, a mitochondria, it's the energy house, right? It's literally what's getting power. You can call it an active component. Your cells, which really just use the energy to do stuff, you're the ones that go through mitosis and stuff, they're passive components. Does that make sense? So that's what I meant by analogies. That's a great analogy, right? Okay, so the reason I want us to be able to read data sheets is tomorrow. I want us to look at a microcontroller. We'll go through Tinkercad. We'll just select a microcontroller that we like. I think there are only two or three, but we'll select from one. We'll open the data sheet. We will all have it open in a PDF editor. We'll go around classifying the components on the microcontroller as active and passive. Ouch. Active and passive. And then we will go on to actually build something with it. And I'm super excited. Tomorrow, 2 hours, it's going to be a fairly packed session. But today, ask as many questions as you want, play around with it so that we are clear when we do it tomorrow. Okay. I would have loved to walk us through some basics of ADC and DAC, but that's okay. Worst case, we have a hardware session that I did last stream. If I can't cover it in time, that you all can always refer to. Okay, we actually went on Jamboard and made all the signals and everything. Okay, so let's go. I'm gonna go right ahead. Click on my dashboard. Okay, click on new circuit. We are now going to make two circuits, one parallel, one series, and understand why I would make a parallel circuit, when I would make a parallel circuit, or connect a component parallelly versus in series. All right. So, can anyone remind me what was the thing that we observed in series versus parallel yesterday? Why were we connecting the multimeter parallelly for the voltage and in series for current? Anyone? I'll give you all 1 minute if anyone wants to answer. If not, I will go ahead. All right. So, if no one's answering, feel free to still answer. Y'all can give better examples and analogies. Take your time, Yash. All right. So, Yash is typing the answer. Uh, I'm looking at some Discord chats. Does it? Voltage gets divided in parallel, or does it not get divided in parallel? This is true, right? So that is what we looked into yesterday, right? The reason why we connected our multimeter, if you want to measure the voltage of something, right, we connect it in parallel because the voltage across it remains the same. So we know that that's the correct voltage because we know that according to the principle of electricity, it's going to come out, the voltage is going to be the same. Current, however, gets split parallelly and it remains the same in circuit. So when the current starts off, the current will remain constant throughout the series circuit. All right. So when we want to measure current, we connect our multimeter in series. Exactly. Uptake, did that make sense? Your voltage does not split parallelly. It splits. So if you measure a series circuit across every component, there'll be some change in the voltage. But if you connect components parallelly, there'll be no change in the voltage. The voltage given will be the same. Now, can you give me an example of when I would want to connect something in series and something in parallel? Give me a very simple example. That's all right, Aptak, which is why we're here. I'm glad you at least tried to answer. That's amazing. Right? So, can you all tell me when I would want to connect a component in parallel versus in series? That is amazing. Yash remembers a lot of basics. Okay. I like the thought, I like the train of thought and the direction of thought, but I want you to complete that thought. So it does not depend on the component that's using the energy. It also depends on your energy source, right? So let's say I only have a 9.9 volt battery, right? That is a good example, and this is actually a concept used in AC, in your electrical engineering. Things are connected as much as possible in parallel, so that even if one of your something in your circuit gets shorted or gets blown up, your rest of the things remains working quite well, right? But in your electronics, of course, that's a great reason to put it in parallel. Why you want to put it in parallel or series is the reason I want you all to think of on the lines of is the resource management, right? So let's say I only have a 9 volt battery, right? And I have three LEDs, right? Now, if I connect them all in series, what's happening is they're getting voltage drops, which is great. So now my entire voltage will be used by three LEDs. If I connect them in parallel, however, they won't work. They will work, but they'll blow up because all of them are getting 9 volts of uh, power, voltage, right? 9 volts of potential difference. Now, on the other hand, if I have three LEDs and one coin cell, if I connect them in series, none of them will light up because the 3 volts is getting divided across the three LEDs. If I only have a coin cell and I do want to light up three LEDs, I'll connect them on in parallel. Now, what will get affected here is, of course, the time that the battery drains in. But this is what I meant when I said, why do you want to think of it? So let's try it, right? I am gonna see if we can demonstrate that. So we have 3 volts of battery. We're gonna take one LED. I'm gonna change the color to yellow. Second LED, change the color to white. Third LED, change the color to green. All right. Right. So now remember, positive to positive. The next negative will go to it. This positive. It's in series. Remember, so series connection. Positive goes to negative, negative goes to positive, and that's how the thing works, right? My cathode will finally get connected to negative. How do you know that you've done it right? If your final uh, uh, connection is negative to negative. That's how you know you've done it correctly, right? So I am going to go ahead and make it a tad bit neater. And remember, what is the first thing that we spoke about today? Some good practices, right? So I'm going to go ahead and do that, right? I'm going to make this the color red and this the color black. There we go. Now these I'm not concerned because they're connected interchange like internally, right? All right, let's see if this lights up. It barely lit up. There is some difference, but it did not light up. Now let's do the same thing and connect this in parallel, right? So how will parallel connection work? How will parallel connection work? Let's stop the simulation. And you know what? I'll just create a new circuit altogether so that we can see the difference, right? So coin cell, LED 1. Let's let this be red. I'm going to change the direction from now on itself. Ah, second LED, blue. And let's change the direction again. Doesn't the blue LED look bigger than the red LED? Is it because it's selected? Yep. Okay. And then last one, I'll make it orange. I think we've used up all the colors, so no colors remaining now. Let's make this again. Good practices. All our positives will get connected with red. So let's start. Red. So this is me connecting it in parallel. All the positive gets connected together and all the negatives get connected together. And again, what we're going to do is we're going to change these wires to black. Right, so select. I should have done this before I connected, yes. But it's a good reminder. Black and black. Right? Now let's start the simulation. You see the difference, folks? Why you want to do it? All right, this is a fun learning. Now you all know one of the good reasons why you want to connect it in parallel or series, right? This is one of the major reasons is resource management, right? When you're connecting stuff, especially when it comes to batteries. Uh, Now is the fun time for you all to try this out. Play around with the LED colors. If you all want, put a resistor in parallel and series and see how much of a voltage drop and a current drop there is, right? And you know what to do. Go ahead and post your circuits in the Discord channel. It's 10:43 on my clock, and let's give you all 5 minutes to get through this. All right. So take 5 minutes. I'm waiting for you all to respond with your circuits. I am excited to see your circuits and see what you all do with the LED structures. I am looking forward to seeing the red and black good practice. And if you all want to go ahead and measure the voltages and voltages across the multimeters, I'll be more than happy to see that. All right, folks. So, why don't we do that? Why I'm gonna wait for you all to do this. I'm gonna quickly again take a quick water break. Right. So it's 10:44 on my clock. I'll be back by 10:47. I'm glad you're feeling good about your 10th poets, Yash. Okay, folks. So I'm gonna quickly be back in 3 to 4 minutes. Take your time. Ask me to wait whenever you want to. Next, we will go on. Just quickly use the multimeter, and then I really want to quickly look at some graphs for components. And once we do that, we'll be ready, almost ready for tomorrow's session. All right. All right. I'll be back. I just saw a question. So, what do you want us to add to the circuit? So, multimeters way. We want to see what's the voltage across the LEDs that aren't being able to light up and the current across them because there's something still flowing. Remember, the circuit's shorted. So there's something, it's just not enough to light up the LEDs. And then use the multimeter to see the voltage and current across the LEDs in the parallel circuit to see the value difference if you all want to do it. I'll do it very quickly and I'll do it for everyone. All right, I'll be back. Take a right, folks, how's it going? Are we done with the multimeters? Or did I see a question from Yash? So, view series if we want a lot of current and parallel, we don't want power source. Here's the thing, right? What is power? Power is basically your multiplication of voltage and current, right? Of course, not directly, but it is directly, right? It's VI, right? And the reason why it doesn't really make a difference, it's not okay to say that it's you're putting pressure on one or the other, is because in one you have a higher current, or rather a constant current and a split voltage, and in the other you have a constant voltage and a split current. So it really depends on your components. Let's say you have a high voltage, right? Let's say you have a 9-volt battery and you need to give the 9 volts to the motor, but you do not want you want an led, you want an indicator when the motor is running, but you obviously cannot use one led directly to the 9 volt, right? So you can use a resistor, of course, or you can use three leds in series. And even when you use the resistor, you'll connect it in series. On the other hand, if you want to run three motors with that same 9 volt, you'll have to connect it in parallel, because even in series you might get a good current to run one of them, but you want the voltage. So the next parameter is whether the device is current controlled or voltage controlled. led is voltage controlled, hence the difference in voltage here makes a lot of difference. Make sense? Yash? Oh, Karuna's already here. Karuna, I'll be freeing up the session for you very soon, don't you worry. Uh, Great. So now I'm gonna go on Discord. Tactic has posted it. That is awesome. And he's also used multimeters and the best practices. That is awesome, Tactic. All right. Now I'm waiting for the other folks to quickly post. I know at least two others are following. So I'm gonna wait on them. LED is voltage controlled. Yes, which is why our voltages here is making a difference, right? Because the voltage drop across the LED is not enough. Transistor is current controlled. MOSFETs are voltage controlled. I think those are good examples. Let me see if I can pull it up. Oh, I'm sure you can still catch up, Karuna. We have almost 10 to 20 minutes more of today's session and over the entire session of tomorrow left. Motor is not voltage controlled. Motor is actually it needs the voltage difference. It's actually current controlled. I'll tell you why. Because we have coils inside it, right? And the coils actually use the current. So motors will be current controlled. But let me quickly check for you. So I just looked it up, and I like the enthusiasm and the uniqueness put in here. Oh, ways done as well. Awesome way. I love the circuit. I love the arrangement of it as well. A Jackson has obviously done an amazing job as well. You know what I'm going to do today? I'm going to actually download all these images with your names and send it to Mary for our daily GHW. This is so cool. This is so awesome. I totally want you all to show off. No worries, Jayesh. Take your time and welcome back. How it isn't, see, again, that's the thing about learning something new, right? Especially if you think it's unintuitive, when you start observing things, like when I talked about passive and active components around you, I hope the next day, during the day, you looked at something that's using battery or something, and went, Maybe this is an active component. Or that's the thing about observing. Next time you go, you'll see that an LED is not bright enough. You'll be like, there's not enough voltage in it. These are some things that you develop the more you think about, and then the more you observe around. So I am counting on you, Yash. I'm pretty sure you'll get there. I agree, Jackson. I agree. Although, if you all are planning to go ahead and get some LEDs and stuff, let me know. I staff Fake pages all the time, and we have something called the Content Launchpad that we haven't used yet. So, if you all want me to do a quick session and you all have the components, I'm happy to walk you through the real components as well. Where's Anurag? He's not using real components today. It is to please do not breathe fumes if things burn, okay? Especially electronics and semiconductors. That is bad. Karuna is a true tinkerer here, right? She's a true maker. This is the stuff I would love for you all to try without being hazardous to yourself, all right? Delicious, where are you facing trouble? Do you want to quickly hop on the stream and share your screen? We can help you out. In your battery, there'll be a plus and a minus, all right? Delicious. Oh, delicious. My bad. So, delicious, there's a positive and negative to your battery. Now, I did not explain this today, which I should have, which is my bad. If you look at your LED, you see there's a tiny turn here, right? The turn part, which says anode, is the positive end of your LED. And always your positive end of the LED and battery, the positives get connected. Your LEDs, if you connect the positive to negative, it becomes a series circuit. If you connect positive to positive, it becomes a parallel circuit. Now, if you're connecting the negative, but the negative part of the last LED, whether parallel or series, will always go to the negative end of the battery. The voltage here will only define whether the LED is bright, does not glow, or blows up. But don't worry, it's a simulator, so you're good. Oh, that's all right. I'm looking forward to you recreating these circuits later, Anurag. Wow, you burnt a Raspberry Pi, Yash. That's a story I want to hear. So you cannot the thing about that's a good part about Raspberry Pi. The GPIOs are controlled to 3.3 volts, so you usually cannot blow up components except if you connect them the other way around, which I mentioned is very common. Ah, well, you live and you learn. I hope that made delicious. If you still have questions, do let me know. I'll show the entire connection again. All right. Awesome, folks. Let's move on to reading about components and data sheets. So I hope parallel and series make sense. If you all want me to do a couple of more examples, we can do them tomorrow or today. However, we have another 20 minutes on hand, so we're good. All right. Perfect. Let's move on to reading about data sheets. So let's start with something simple, right? What do you want to start with? I would say let's take something not let's do three readings. Okay, let's read one a passive component, one an active component, and one a fairly complicated thing, which is not like okay, TK, you connect it and it lights up, right? So we'll do that. All right. So I love the discussion going on. I love the hardware discussion going on. That's awesome. But question for you: what passive component do you want to start with? We have capacitor, inductor, LED, resistor. Okay, before I forget, I'm going to write down the agenda for myself because I keep losing track of it. So we're going to be doing LED. Everyone wants to read about an LED. So I'm gonna go in my browser in the same tab that I'm sharing. So I'm gonna go ahead. I'll share this tab where I googled what's a ferret wheel because I wasn't sure. And I'm gonna go ahead and click LED data sheet. Now, there are tons of types of data sheets out there. All right. So, couple of quick notes, right? Uh, Never go to all data sheets, right? So there's something called all data sheets. I'm very glad it's not in the top search, but it usually is. Adafruit, Spark Fun, great places to go learn something, especially if you're starting out. Way wants to read about an inductor. I'm so glad you said that way because I want to explain the inductor and capacitor curve anyway. So we will go with them. Might not the maybe not the data sheet, but more of the concept at the very least. All right. Right, so we're gonna first look at the simple, nice explanations of the Adafruit folks. All right, and then we'll look at a real data sheet, right? There we go. You can download the data sheet we'll be referring to here. So, what these people have done, these really nice Adafruit people, they've actually gone ahead and simplified this very, very technical data sheet for you in the article. All right, so let's go back here. I'll open this in a new tab and we just go over it, right? So what does it say? Okay, we know that the mighty LED has its limits, right? We already know that. We saw how it does not light up when we give it low voltage. This sheet is for the 5 LED. Remember, there are LED sizes, right? And there are tons of packages also. Uh, that on that note, I'll show that to you later. So this is something called a PCB ruler, right? So if you see, these are how tiny LED packages and resistor packages get, right? You see all these sizes. These are how tiny the LEDs get. And this all, whether that LED is available in the size, what's the package, what's the thing, everything is mentioned in the data sheet. So let's say you are designing a circuit, uh, right? You want to be able to see if it's a product, right? If it's a watch, you cannot have LEDs poking out from it, right? You know those really nice sophisticated LEDs you get on your watches and your phones. They're all SMD LEDs, surface mount device LEDs, and like they're usually in this size, right? In this size. So how does the designer decide this? They usually have reference. They Every company releases its catalog with different sizes, and when they're designing, they decide, okay, this is the size my PCB needs real time. Then they go online, find the library of that company, and then actually use that when they're designing. Okay, so this is a great reference PCB. If you all ever meet me, do ask me for this. I always have this on me. This is from my company. Okay. All right, let's move on. Yash, that's a good question. So the reason why all data sheets is not great is because what it does is it's basically like a web scraper and it gets all the data sheets on. So you can never be sure if it's authentic or not. Always when you're looking at data sheets, go to the company's data sheet. Okay, it's more authentic, it's more accountable, especially because a lot of times data sheets get obsolete. The product and the even the LED keeps evolving. So it's good to always go to an accountable site, which is basically almost always the company site. All these good folks, Adafruit or Spark Fun, who do a lot of simplification for us, right? All right, great. So, okay, we now know that the LED we're talking about is a 5 LED. All right, these are the package dimensions. I just spoke about the package, right? So, this is the difference between the cathode and the anode. Why is it important? If I'm creating a PCB or I'm soldering it onto something like this is a zero PCB, right? I need to know that the leads will fit into this, right? So, that's the reason why you want to know the distance between the cathode and the anode. All right, so you can see that the main diameter of the LED is 5 mm. That's how you know that it's a 5 mm LED, right? Uh, mm, so again, this is the same thing that I said. The reason why you want to know is that you want to make sure that so the lip is basically the extra border that's there on the LED, right? So let's see if you all can see this. So this is your LED. You see there's a slight here platform that they've created. It's exactly for that, right? All right, so now there are specification, right? So there are electrical specification, its brightness, and its voltage, its limits, maximum limits, and the unit of the maximum limit, wavelength, forward voltage, reverse current, right? It's a diode, so there is some form of reverse current, right? All right, so they have simplified it down to less than 200 words, right? Now let's look at the actual data sheet, right? So this is the actual data sheet, and you can see how detailed it gets. All right. So we already had a look at its electrical and optical characteristics, its limits. These are the test conditions. It's kind of important. This is the that's the ideal condition that they tested it with, right? These are never the real life conditions. So you can always, how will you verify them? They usually have these amazing graphs that tell you that, okay, we tested here, and according to our observation, this is how the curve will go, right? So you can always look at, okay, so this is my condition, and how much am I expecting the forward current to be? If it's not the same, there's something wrong, right? uh, it's actually fairly easy to check, especially with LEDs, because the checking of voltage and current is fairly easy, unlike most other components, right? Uh, okay, is there anything else? All right, absolute maximum ratings, right? At the temperature, this is the room temperature that they've taken it. Again, your real life condition will never be the same, but these people are nice enough to actually give you temperature graphs as well. They haven't given it here, but usually LED. Yeah, there we go. There are temperature graphs, right? So this is at ambient temperature, and they've given you entire graphs of how it varies, right? So remember to always look at the temperature when you're comparing, especially if you're debugging, right? Data sheets are great at debugging. All right. So this is your super bright red, right? This is like at its absolute highest brightness. This is the DC current you'll get. That's 30 milliamps you need, and the power dissipation is 75 milliwatts. Remember, power is VI, so it's basically both your current and voltage being taken into consideration. Now these people have actually gone ahead, and so this is the thing I was talking about, a different package. So they have different packages available, and you all can always go on their site and order a specific package of the same LED. They have also given you these amazing mounting guides, which a lot of LED datasheets don't, because they usually focus on a lot of other characteristics, right? So this is your LED data sheet. I want to say electronic engineers because we just went over the difference, but I love data sheets. Okay, great. Ask me then, Karuna. But yes, so data sheets are so important, so important. Last time also, when I was taking streams, I always say this: if you have a question for me, especially about a component, the first thing I'm going to ask you is, did you Google the data sheet? Did you look at the data sheet? What data sheet did you look at? Because if you're not looking at the right data sheet, things can really screw up, right? So thanks, Karuna. All right, so let's move on to our next component. Let's look at inductor very quickly. All right, let's not look at, I won't look at a data sheet, but I'll rather look at the characteristics of an inductor. Does anyone know how an inductor works? And a capacitor for that matter. Anyone? Why do we need inductors and capacitors? What do they do? No, no one? That is interesting. I like how you're using Three Idiots jokes here. Yash. All right, let's not waste time. Uh, it's okay. I'm a very nice teacher. If you do make eye contact and look at me with, I have no clue, I'll explain better. Let's go here and look. Let's quickly look at an inductor. Okay, so I don't like this. This is my favorite explanation of what's an inductor. Okay, so we're going to look at this. Okay, so what is an inductor? Why do we need an inductor? So here's what an inductor does, right? I'll just put this link because this is my favorite website for inductor explanation. I was recently explaining it to a friend, and here's where I went. That's a great answer, Uptak. Capacitors store energy. Do you know what? Inductors do the same thing. Inductors do the exact same thing. They store energy, just in a different way. All right. So both capacitors and inductors store energy. So if you all know, capacitors have two parallel plates. Okay, they're almost there are these dielectric components, right? So there are two plates, and these plates are charged, and when they're charged, they have a force, and these to charge them, there's a force that required. So initially, if you realize, hmm, did the link go through? I hope the link went through because it's showing me an error here. But so there are two plates, and you're basically trying to build up charge on both the plates, right, and create a potential difference. Now, what happens is when you initially connect a capacitor in a circuit, there is a point. Thank you, Way, for confirming. And thank you, Yash. Uh, Thank you, Karuna. And so these are two plates, and every time you connect a battery, right, for the first very tiny seconds, there is a very low voltage in the entire circuit and a low current before the current goes back to its normal state. Rather, it goes in the way that you would have ideally predicted. Why does that happen? Because the first few seconds are spent in charging the capacitor. When I say first few seconds, I'm exaggerating because it takes very less time, right? Like a second, it's usually nanoseconds, all right? The charging. So as soon as you connect the battery, these plates get charged up. Now, what happens is usually capacitors are connected in parallel. Why? Because as soon as you remove the battery, right, these capacitors have charge that is built up on them. They've stored the energy. Now, these act like flashes, like battery flashes, and they immediately give a peak current. And this current is what gives the power to the circuit for a few more seconds, right? Now, this is usually few seconds. So the discharging time is usually a little higher than the charging time. Exactly, they're dielectrics, right? They're dielectrics. Now, here's a fun fact for you to remember why capacitors are important. You know, when you in your laptops, when you have your where your cache is stored, right? Where if your power goes out suddenly, how does your memory and everything get saved? This is how they get saved, right? You have a capacitor which is connected in parallel. So if you lose power, the capacitor gives the chip enough power or power for enough time to be able to save everything and then lose power. Isn't that awesome? Isn't that cool? So why don't we use an inductor? So here's how inductor works, right? Inductor does the same thing. It stores energy and it gives out energy. The only difference is capacitor gives a burst of energy. It gives a lot of power in a very short time, right? An inductor, on the other hand, is basically a coil wound around, right? I told you inductor is similar to a transformer. It's nothing but a coil wound around, right? And that coil wound around has a magnetic field, all right? As soon as you give it power, the current is inhibited for some time because the magnetic charge is inhibiting the current. The current still going through is creating an EMF. That EMF is the energy, that new energy that is being stored, right? Now, as soon as this EMF has reached its full potential and it's constant, the current will go back to its normal state. So the same way as a capacitor. So now it's going to start its charge now, right? Now, as soon as you remove the battery, this inductor is again going to give a current. But here's the thing, the inductor is going to give a smoother current, right? So it's going to last for a longer time, but the value is going to be a little less, so the power will be lower. Some, not exactly. The USB is very different because it's a huge entire circuit that's doing that. The capacitor that I spoke about is in your laptops right now, right? In your systems right now. It's an internal mechanism that your laptop companies give you. So if you power it off immediately or suddenly there's a shorting or something happens, the chip will have enough time to save everything it needs to, or it has been asked to save. Make sense, folks? All right, I isn't that awesome? I find the working of inductors and capacitors very cool. So here's what I'm gonna do, right? This is a really nice website. I love the explanation that they've given here, especially over here. This the material part that they've explained, and so you can see inductors are used with capacitors to kind of smoothen out. Inductors are used in filters to tune things out. I am also going to turn around because my battery in my laptop is low. But isn't that very cool, folks? I love talking about inductors and capacitors, as you all can tell. Okay, so I'm going to quickly do one last thing. I'm going to look at RL analysis of curves, right? So let's quickly pull up a graph, and Karan, I'll hand it over to you right after that. More like I'll close the stream so you can quickly start yours. Where is the circuit? Okay, so this is the RC circuit that I'm talking about. So it's usually called an RC circuit because when you study it, it's always in with a resistor, so that you have a control over the voltage that's going. And so this is the RC circuit. This is how it works. So when I spoke about circuit analysis, this is what I meant, right? So I'm just going to quickly turn around so that my battery does not run out, but you'll get the point, right? So, okay, I'm dark for a bit, but that's okay. Y'all can still hear me, so we're good, right? So, right. So this is our RC circuit curve. Y'all can see. My bad, folks. Right. So you can see at t1 at exact zero time, the everything is zero, right? At exactly t, 0 plus tiny t, it goes up. The voltage of the capacitor goes up, and your current slows down, right? It slows down, and it goes down when the voltage is charged, the capacitor is charged. And if you continue, right, after the discharging of it happens, the discharging happens like this, right? It peaks, the constant of time, constant in RC circuit, right? So the voltage peaks as the time goes, but the current will peak and then reduce, right? So no, I don't want to read about R constant. I want the RC discharging curve. Can I see the RC discharging curve? But you get the point, right? So that's how your peak, that's how much it varies. Now I'm going to search for inductor charging discharging curve. So inductor charging discharging curve. So this is the one. I like the one which has MATLAB. Also, even all about circuits should have a good one, but I usually go for the websites that I trust, which is usually like MATLAB and things. There we go. So you can see inductor voltage is a much smoother curve, right? Unlike your capacitor, which had a sharper curve. Don't want to subscribe now. And no discharging curve. I don't like that. So this is what I'm looking at, right? So you can see that this is a longer and a smoother curve than a capacitor, right? So this is all I really wanted you all to see today and understand. I know we're still left with two data sheets, right? One of the active component and one of a slightly complicated component. But we'll just look at data sheets as we go tomorrow, right? Are there any questions about today from parallel circuits, series circuits? I would love to see you post your circuits also on anywhere, actually, Twitter, Instagram. I know one of you all shared it on Instagram yesterday. I was so glad to see that. So in case you all are sharing, here you go. Do tag me. I would love to reshare. And if you all are still completing your circuits and posting on a Discord, definitely tag me. I'll download it and send it to Mary. But awesome. It's not an exponential curve. No. What I meant was it happens very quickly. My bad. My bad. It's not an exponential curve. I am trying to do that as well. I'm going to be attending a hackathon happening in on 3rd Feb in Gandhinagar. If you can make it, Yash, nothing like it. Same here, Yash. I would love to meet all the hackers in person at some point. I know I'll be in Kolkata for a hackathon end of Feb and in Gandhinagar in start of Feb. And I'm also staffing an FPH in the 3rd week of Feb, I want to believe. But yeah, I'll be in hackathon soon. I know I was completely gone December and I did not have much in Jan either, but now I'm back. So sure. Okay, let me have a look at Discord very quickly. Where am I supposed to be looking at? Wait, what channel did you post the question on? Oh, perfect. I'll definitely meet him there. I'll see you in Kolkata indeed. Wait, I can't find your question. What channel did you send it in? Did you create a ticket? I cannot see your question. Oh, okay. Oh, I see the question now. My bad. Why is everything zero when I change it to amperage mode? Because there is no current flowing, right? There's been a voltage drop in the total. So remember, your current will be V by R. If the R is too much and the division is like, because you have too much resistance there, your current is become close to zero, right? Does that make sense? Way so you have voltage 3 volts. You're using LEDs that have almost exactly too much resistance. So your R is value. So it's not zero. It's just really tiny. There is some current for sure, but it's very tiny. So hence negligible. The other explanation is because the resistance is too high. There is not enough potential difference for the current to flow through. Right. That's another way to look at it. So because the resistance is so high, there is again something flowing through it because it's a complete circuit, but it's too low for it to actually pass through and complete and actually travel through. I didn't see your question, it was above the picture, so I saw it now. Awesome, I hope that answered the question. uh, so I don't know what you mean by circuitry. There is something called ULP and Eagle that is used for automating some circuit stuff. I usually use embedded C and CPP in IDEs like Arduino IDE or a program. I forget the name. Program.io. I don't remember the name. I'll come back with the name tomorrow because we'll use it hopefully. Platform.io. That's the thing I'm looking about. So platform.io is a great place to get started as well. And yeah, usually C and CPP are good, but you can also use MicroPython and CircuitPython if you are good with Python and you want to continue embedded systems with Python. You can also do Rust. I know for a fact that Jim Bennett has started a new series on Twitch where he's learning Rust for embedded systems. You all can join him as well. All right, folks. Karuna needs to start in 8 minutes, and there are streams back to back today, so it's not like I can take my sweet time and then Karuna can extend it. So I'm gonna go, but I'll see you all tomorrow bright and early at 10:30 a.m. I get an extra hour of sleep tomorrow, so I'll be slightly happier. And yeah, I'll see you all soon. All right, bye, folks. I'm gonna end the broadcast now with some tunes for like a minute. Bye bye.